Okay, welcome everyone. Welcome to QuickStream's Academy episode 3. Today, Thomas is going to take you through how to downsample real-time data, real-time time series data, in fact, using QuickStreams, and also how to persist it to an InfluxDB. Take it away, Thomas.
Thank you, Steve. Thank you very much. So today I want to discuss time series data, how to recognize time series data, and how time series data looks in the database, and how they look in Broker, because that is a different story. And then we're going to talk about pre-processing and why that's useful when you're ingesting data into your database. And we're going to discuss why you want to use time series database, what are the motivations there, and what are the benefits of using time series database to other types of databases. And then in the pre-processing part, we're going to go through a common task that you might want to do before you land your data in your database, like data normalization that we did in the previous episodes, and downsampling when you want to reduce the granularity of your data. And then we're going to discuss the architecture and how the stream processing goes hand to hand with the database and what benefits that gives you, and some of the more advanced features of that, like backpressure. All right, so for those of you who have not seen my previous episodes, let me quickly introduce myself. I am Thomas Neubauer. I'm CTO and co-founder of Quix. And I have spent my whole career working with real-time data, mostly with a sensor data coming from a cars, which of course is time series data. My last project before Quix was in motorsport, where we were building a telemetry acquisition pipeline of a time series data coming from F1 cars in McLaren, and building real-time decision insights into what's happening on the track to help people decide in the garage in a split second. So what is time series data? And how that goes hand to hand with streaming data frames that we have discussed in a previous episode, which is the major feature of our open source library QuickStreams. Well, this is how the time series data looks like when they are static. So for example, in time series database, or just in an Excel sheet, or maybe just in a pandas data frame loaded from CSV file. You usually have a time column or time index, and then you have a set of measurements that evolves over the time. So it could be a temperature sensor, or in this case, accelerometer, which gets measured in intervals, which could be periodical or not periodical. And then that value basically evolves during the time. Now, if you struggle to really make sure that you're looking at the time series data, there's a great validation tip. If you can visualize your data on a waveform where horizontal axis is the time, it's quite likely time series data, because most of the time series data can be represented that way. Now, it doesn't necessarily have to be just a number. So here, obviously, you see that we're looking at the floats evolving during the time, but it could be a enum, for example. So just a couple of values rotating during the time frame. All right, so this is how the static time series data look like. But this is how the time series data gonna look in streaming. Now, each message gonna carry a portion of this time series data. Quite often, you will get one timestamp per message. And then you need to somehow compose this into the original big table that we see before. And sometimes it's not as easy, because sometimes you get multiple rows in each message, and you get different number of rows in each message. You see, that is a challenge that we're going to solve today together using QuickStreams library. And let's go to the code and just have a play with that. So we're starting where we end in episode 2. Now, if you just happen to join us for episode 3, don't worry. There is a Streaming Academy GitHub repo, and in the main branch, you have all the commits of all episodes. So you can always go back to, let's say, episode 1 and repeat episode 2. Or if you want to do episode 3, you just go to the commit of episode 2 and follow me as I'm building this downsampling pipeline. All right. So here I'm having the same project that I had before. So I have the replay of my producer, and that is sends data coming from the phone. And then I have a data normalization service, which taking nested JSONs into more tabular, more time series data, if you like. So let's run the service, and I'm just going to change here consumer group to def, and do the latest here. And I'm going to go and run the producer again. So raw replay Quix space run. Good. So now, if I go here and go to data normalization, and now I do a Quix space run, sorry. And I make it a bit bigger. Great. So now what you see is this data. If I stop this and I move to the very end of this topic, so we see nicely how it's changed in a real time. Great. So every second we get a message which represents one row. Now we have got multiple rows in input message coming from the data source, but if you remember in episode 2, we have solved that, and now we're sending each row as a message. Now you see that the whole virtual table just scrolling, and that's what we call streaming data frame. And we have discussed it in episode 2 and episode 1. Please check it out if you want more details. Now, you might be asking, what is this blue table? It wasn't there before. Well, this is what I added for episode 3. Check the GitHub. It's in a console. It's called console sync PI. It's just a pretty table open source package that's helping me to visualize data in the broker in this nice way. All right, so we have this working. Great. So let's create a new terminal, and so we can continue. So going back to our slides, let's discuss what is a time series data and what it's not. So sometimes time series data are a bit hidden behind lots of JSON source, for example, here. So you might be thinking when you look at these messages, well, they are actually not time series data, but they are. Because if you look this highlighted number, it is evolving over the time. It just happens not to be sent in a tabular, nice format, but that's quite often the case. So this is still time series data, and we just have to unpack it from the JSON to send it more efficiently. But this is not time series data. There's nothing to evolve really here. We just have a user ID that just registered. This is just typical message payload, which happens to have a timestamp. But timestamp data is not equal to time series data. So here we have a timestamp and we have not time series data. Having said that, we can make, with some transformations, time series data from this as well. For example, we can, say, I'm interested to know how many people in Springfield register every hour. And suddenly, from completely not time series data, we're getting a time series data. There's always opportunity to get time series data from our input topic. All right, so let's go into time series databases and why they are interesting in our project. Well, Time series data is often what you're going to work with when you're building stream processing pipelines. And so when you happen to get into the point you want to sync them to some database, time series database might be interesting for many reasons. The first reason is that time series database is optimized to process time series data in terms of storage and query. That means the data get compacted compared to relation database, and they are optimized to query fast data based on the time index. So here we have a simple query where we're just getting last 24 hours of our data, and we have a couple of columns. Now, I ask you to sign up for Quix Cloud. Now you can do that and get a free 30 days trial where you get Influx database and you can sync data from your pipeline into it. So here I have my table, and if I just copy this query, I have to just exit the slideshow. But if I copy this query here and maybe put 3 days, there we are. So we have nice result from the database. Now, if we go back here, we can go further. So this is just a simple query. But what if we want to do aggregation? So here I'm asking the database, give me how many rows and average of a column G mean for this period of 24 hours. And again, because it's indexed by time, this is a fast query, despite it might be scanning a lot of items. And this query will not degrade at the rate that it would degrade in other databases, even if you have years of data and billions of rows. All right, we can go further than that. We can say, give me 15 minutes time brackets with this exact aggregation. If you do that, you will get a result that looks like this. Every 15 minutes, there will be a timestamp and a row with aggregation for that particular bucket. In other words, each time bracket contains one or more rows, in this case, usually around 30. And then here is a calculated value for that bucket. Okay, so before we can learn data into our database, we're going to have to do some pre-processing. So first, we already have done the data normalization. So we have done that in episode 1 and 2. And basically, we converted this rather difficult JSON, nested JSON, into this nice tabular format. And the second thing we're going to do today is we're going to reduce the granularity of our topic, because we are getting like 4 or 5 rows per second from our phone. If we persist that in a database and we get hundreds, thousands of phones recording all the time, very quickly we would fill our database with lots of data, and we would just be paying for a lot of storage and query time, despite we might not need that granularity in our analysis. So what we're going to do today is we're going to build another step in our pipeline, because in a future episode, we're still going to use the original high resolution data for anomaly detection, and we're going to plug the AI ML model to it, etc. But for analysis, maybe that will be too much. So we're going to reduce it to 10 seconds intervals. In other words, we're going to have one timestamp per phone per 10 seconds. So we're going to reduce the number of data, amount of data, but more than a factor of 10. Now we're going to use what we have discussed in episode 2, which is a stateful processing service using tumbling window aggregation. And we're going to use all the features we have discussed in the previous episode to deliver this in a scalable, fault-tolerant, in a resilient fashion. So if you go back to code here, and I do Quix apps create, we want to create a new transformation. We're gonna call it downsampling. We're gonna read a table data. So this is the result of our normalization service. And we're gonna create a new topic called table data 10 seconds. Great. So let's go to that service and let's borrow this console sync file into our downsampling again, so we can use it. And here, let's call this a downsampling service. Let's connect to the end of this pipeline. And first, let's just print what we have in our topic. So let's create a new instance of our console thing. Now you can find this in GitHub, but if you don't want to use it, you can always just print it as we did before. Great, and of course, we don't want to output data yet. So now if I do a Quix run, and I'm gonna run the producer, great. So this is data we're getting. And as you can see, every second we get one row. That's too much. So let's stop this and let's do something with it. So here we're gonna start with doing SDF equal SDF.tumbling window. We're gonna import two important packages, two important classes from data time delta and datetime. So in time delta, we're gonna do a 10 seconds bucket, and we're gonna wait 5 seconds for late arrival data. And now we're gonna reduce it with our custom aggregation. Why are we not using built-in function? Because we want to do something more complicated than just min or max. All right. So first, we're gonna define a reduce function for window. So reduce window. So here, first parameter is a window, and the second parameter is a new row coming into that window. So this is a callback that you will get for every row that window. So first thing we're gonna store is gsum. So we're gonna sum all the g-forces. Now, in order to do that, we need first to calculate that. So if you remember from the previous episode, we did something like this, and then we remove it from the code base. Let's put it back. This is basically a in-memory feature computation, the most basic stateless operation we can get. With this, we collapse 3 columns into one to make this a bit more compact. Okay, so now we're gonna reduce this G total into this G sum. Maybe we are also interested to know what was the maximum G forces at that window of 10 seconds. Well, for that, we're gonna do window G max. And we're gonna do something like this. We're gonna reduce this number to one that's bigger. So if there's a bigger number in the window, we're gonna keep that. But if the new value from the new row is bigger, we're gonna replace that value with a new value. Okay. And lastly, to be able to calculate average, we're just gonna do g count, like we did before. And then we also want to keep our aggregate at GPS location, because we want to look at the data and analyze in what part of the map what g-forces were applied to the phone. So here we're going to use the last value of GPS coordinates. So that's going to be easier. And the same for longitude. All right. So now longitude. Yeah. So now we're going to return this window and we're going to continue to init. So every window needs to be initialized. So what you're going to do with the first item in the window. So here I'm going to do init window, where we don't have any state yet. And I'm just going to return the initial value. So again, we're going to have a gsum. At this point, just equal to this. The gmax is going to be the same because a maximum of one value is that value. The g count is going to be 1, because we can just have a new window with one row. And the same is here for GPS coordinates. All right, so now we are ready here to just call it in reduce function. So we're going to do reduce window and init window. And lastly, we are interested in only windows that have been completed. So that means that there is no other changes expected to that window, which in this case is going to be 5 seconds after the last value, where in terms of timestamp arrived. All right, so that's it. The last thing we need to do is just to make sure we have these columns to be using, because they might not be in input data. For that reason, I'm just going to do SDF contains the accelerometer. And we also want to contain the location data. These are two modules that are not necessarily coming together. All right. So now let's see if this is going to work. Okay, so now we see we're getting data, and every 10 seconds, we're going to get a new row. If I enable the produce again, every 10 seconds, we're going to get a new row in this output table. Now you see that that value is what we are reducing in our reduce window. So that JSON with 5 properties, gsum, gcount, gmax, it's there. And now you saw it moved. So let's unpack it to basically get that JSON into the columns. So each property in the value will have its own column. So we can output it in the output topic. Great. So I'm going to stop this and do that last bit. So after the stateful operation, I'm going to do apply. And here, the first thing, we need to define what is the timestamp. Usually the end is the best way to use. Now that's also by default what is set to a Kafka message. But here, just for development purposes, I'm just going to create a time property, which I'm going to make a bit more human readable. So I'm going to use here the row end. And actually, this is, yeah, in milliseconds. So I need to divide it by 1,000. And then I'm just going to unpack the value. So basically, I'm just going to move this into its own columns. So let's give it a try. Amazing. So now you see that the time column gonna have a value every 10 seconds. And now we have a gsum, gmax, gcount, and etc. Now, of course, what we can do now is calculate the g average, because we have the count and the sum. So we just can divide those two columns. So what we can do here is, instead of maybe this, we can do g average equal and then we unpack it. Let's see. Let's make sure we getting the data. Great. So of course I have forgot the value here, so that would not work because we haven't unpacked it yet. Great. So now we see that the G average is ready to be persisted. So now we are happy with our data. I'm going to stop this service and I'm going to do last change, because we don't want this pretty table in a production service. We're just going to do SDF print, and we're going to uncomment that. Great. So let's run this. And let's go back to our slides and discuss how we're going to persist this in an Influx database. Great. So let's discuss the architecture. So what we have done is basically we have added a new microservice called Downsampling that's consuming the table data topic we have created in the last episode. And it's now outputting data to a new topic called table data 10 seconds. Now that is here, as you can see, produced into a topic called table data 10 seconds. So if I open it in a Red Panda bit, now you see we have these aggregations. And if I get here, again, the aggregations. Great. So we have the data. Let's go back to our slides. Let's discuss why we're doing this. Why we're not just saving data in downsampling service or data normalization service. Why are we producing another topic here before we sync it to database? Well, it's because equally as we want our data normalization and downsampling to be resilient, fault-tolerant, and scalable, we expect the same from our syncing. And so what we're going to do here is we're going to use Kafka log and consumer groups in the same way. It's just to be output is going to be Influx database, not a topic. So let's go into our code. Let's create another console. And let's go to Quix apps, create. But this time, we're going to use a different template. Explore more items. We want to get a list of our destination. And here we're gonna use InfluxDB 3.0 sync. Now, pay attention to the version because you might be using 2.0, but I'm using the latest Influx Serverless Cloud 3.0. Okay, the name, that's fine, I can keep that. Now it's asked me what input topic I want to sync. Well, I'm gonna use the table data 10 seconds. Now it's asked me for the host. Now I'm not running this one because it's a European one, but my demo is running in US. So that. Now the token. So I'm going to copy this secret here. And the org is going to be Quix. The measure name is going to be Streaming Academy. No, actually not Streaming Academy. Sorry. The measurement name is going to be Table Data. 10 seconds. And the database is going to be Streaming Academy, not Screaming. And the rest is not important for us. So now if we go to the folder structure again, we can see here environment variables that we're not going to use. So I'm going to delete them and going to keep the ones we need. And that's it. So I'm just going to go into this folder and do a quick run. Before I can do that, I have to just pip install the correct version because this thing is using different version of Quick Streams. And now if I do Quix run, great. So now this is running and persisting the data. And if we go to pipeline, and do Quix pipeline update. Amazing. So this is exactly what we had in our slides, plus obviously the file sync, which we don't need anymore. So we can maybe remove it after this episode. All right. So now this is being persisted to this database. And let's discuss the last bit, why you want to do this. So when you're getting data, they might not come in the same rate. You might have spikes. There might be outages, which are followed by a bulk of data. If that's the case, we're going to use this table data 10s log as a buffer to protect our database from spikes. It can go as far as when the Influx database refuses to ingest data, we're just going to wait, throttle, and try it again, up to more advanced algorithms that monitors the time to persist the data and then try to keep that in a certain range. Now that is called back pressure. So what's going to happen if we have more data that our database can handle? So imagine in this waveform, the epsilon x is a rate of data, horizontal x is a time, and the red limit is how much Influx can ingest. So when the rate coming in exceeds an Influx rate, we're not going to kill Influx database. We're not going to fail this ingestion. What we're going to do is we're going to just keep that ingestion rate in a rate of influx out of possible. And then when the rate decreases to numbers below the line, we're going to persist the spike just later. So it will be landing in the database a couple of seconds or minutes later when we get the space in Influx to do that. And that's the green line. So basically, that's how the back pressure ingestion pipeline equipped with a back pressure mechanism gonna behave, where you have more data than your database can handle. And this is useful not just with databases, but with anything that could be resource limited. All right, so that's all for today. Please check out the GitHub. Here's a QR code where we're gonna commit the episode 3. And so you can follow this video line by line with me. And of course, check the result code if you have any problems or you don't know what to do next. And please check out our videos on YouTube and stay tuned. Thank you very much for today. Bye-bye. I'm gonna check if there's any questions, but
Oh, apologies, I was on mute. I was saying thank you very much, Thomas, for presenting that. And yeah, we'll look out for any questions. So ask them in the comments on YouTube or on LinkedIn. Unfortunately, we had a problem going live on X, but we'll see what we can do about that for next time. So thanks a lot, Thomas. Goodbye.
bye-bye, everyone.